Thank you. It's my pleasure to open sessions with our concentration, as I should say, inequalities of detailed distributions. This is joint work with Paul Guterres, who has been a PhD student of Goethe as well. However, in the field of analytic number theory, and meanwhile he has left science anyway. So, let me start with a classical second order concentration result. So we take n independent, identically distributed random variables which have mean 0, variance 1, and some details, which is what I've written down here, and some symmetric matrix A. And then we want to have concentration inequality for the quadratic form, which is defined by this matrix. And this is the famous Hanson-Wright inequalities, the inequality from the beginning of the 70s, which looks like that. So what do? You center the whole thing, which under the conditions which I've written down here is the expected value is just A. And then you see that you get such a two-level tail bound. Here you have a sub-Gaussian regime, so to say, which scales with the Hilbert-Schmidt norm, which is also Frobenius norm or Euclidean norm, whichever name you prefer. And then you have a sub-exponential regime, which scales with the operator norm of A. Right? And here you have some constant, which only depends on the Ci, so in essence, the sub-Gaussian norms of these random variables. Okay, and this can also be made more precise and so on, but I've just chosen some simple version of the whole thing. And it has a number of applications, for instance, in random matrix theory, in computer science, and so on and so on. So this is some interesting thing. Now let us consider random variables which have tails which are a little heavier. So they are no longer sub-Gaussian, but still sub-exponential in some sense. So you replace the 2 from sub-Gaussianity with some alpha, which now lies between 0 and 2. Yeah? And then there's also a lot of literature around all this. For instance, by Adamczak and Latauer, Kolesko and Latauer, and also some contribution from myself together with Goethe and Zinulis. And one possibility to derive a Hanson-Wright-type inequality for such random variables looks like that. Well, you see it's similar, and what I should also say is that this is not the sharpest version you can get. Yeah? It's just one example, one simple example of how this can look like. Yeah? And the question with which Paul and myself started was now these are these alpha sub-exponential tail random variables. They have heavier tails, but this is not what you would consider to be a heavy tail random variable. Yeah. So what happens if you now take random variables which have really heavy tails? So if they're only polynomially, for instance, classical example, Pareto-type distributions. Yeah. Which have exactly this type of tail decay. So what could be a heavy-tailed Hanson-Wright inequality like? Yeah? And well, to come nearer to this, we needed to study the moments of such random variables, because already in classical cases, for instance, for sub-Gaussian random variables, but also for sub-exponential random variables, if you want to derive higher order concentration results, so for quadratic forms, or also for forms of order 3, 4, and so on, of order D, you typically work with the moments, or the LP norms equivalently. Just to recall something classical from sub-Gaussianity, there you know, of course, that this sub-Gaussian tail decay is equivalent to the decay, to the growth of the LP norms of order root P. Yeah? This is the same. Yeah? It's equivalent. So let us look at the Pareto case. Of course, if you have a Pareto random variable, you can easily calculate these LP norms, and they look like this. So in the denominator you have an alpha minus p, and it is all only finite if p is smaller than alpha. Yeah? at alpha it all stops. And now if you want to go back to the tails, what could you do? Well, typically just apply Chebyshev for any p and optimize the whole thing. And what do you get then? Well, here you have some constant in front, which does not have to interest us. And here you have this 1 divided by t to the power of alpha. But then some logarithm appears. Yeah? So, well, strangely, in some way, you do not get back the tails you started with, but there's some logarithmic error which occurs. And this was the first thing we thought about. Why does this logarithmic error occur? Is this an artifact of the procedure? Is it maybe not strong enough just to apply Chebyshev or whatever? Or does it have to be there? Okay. And for this, we characterized this Pareto-type moment growth. So similarly to all this characterization of subgaussianity, you can say the following. We have any alpha greater than 0 and some random variable x, which we assume to be not negative. Otherwise, you can take the absolute value of it. And then the following conditions are equivalent. First, this Pareto-type moment growth. Yeah? And the second one is, now, as I said, p equals alpha does not work, of course, because then everything explodes. But what you can, of course, do is truncate the random variable and so say, well, I only consider it until it attains the value r. Yeah? And then you take the L alpha norm, so to say, and what happens? Well, the whole thing grows like log r. Yeah? At least if r is large enough. And you can something similar if you multiply it with the exponential of minus sx. And then once again you have something which behaves like the logarithm, now for small values of s. Yeah? And up to now we have not said anything about the tails, and we can actually say something about the tails, but under additional conditions. For instance, if we assume to be t to the power of alpha times well, these tails to be log convex, or to be log concave and bound from below, away from 0, then this is all also equivalent to this Pareto-type tail behavior. However, we do need in the proof these additional assumptions, and I should also emphasize that assuming this guy to be log convex does not mean that the tails have to be log convex, right? Okay, how do you prove this? Just a few notes. Well, what you cannot do, of course, is just take all these phenomena for subgaussianity, as you can read them off in Schilin's book, for instance, and do something similar. You have to change something. However, many of the steps are not that hard. Anyway, where you have to work most is probably how to go from 1 to 2, and this works by characterization of 1 via the behavior of the characteristic function. There you have some identity which involves the gamma function, I think. Okay, and also we can note that by point 4, of course, these assumptions are satisfied for the Pareto distribution, so here we get the correct tail behavior. Anyway, this is this. But nevertheless, the question remains whether there are any random variables which have a tail behavior like that, such that a tail bound like that fails. The first idea you could have is that, well, I take these tails which come out after applying Chebyshev and so on and so on, and just transform this into a random variable by sufficiently renormalizing, whatever. And maybe this is already what we want to have. However, it actually fails. Because if you now calculate the LP norms, you suddenly get a square here. Yeah? So this log t is already too much to get back the LP norms you started with. It's tricky in a way. Yeah? There's always this logarithm, and here you get one step further. Anyway, nevertheless, there are examples which show that such an error cannot be avoided. And I will give you an example now. We take some function g, which is of the form t to the minus alpha, which is what we want to have, and this correction term L of t, which is of the form exponential of some integral of epsilon of s divided by s for some bounded and measurable function epsilon. And if g of t decays to 0 as t goes to infinity, then of course you can define a random variable by this. Yeah? And this is, for instance, guaranteed if epsilon of t is smaller or equal to alpha divided by 2, or any value alpha star, however you want to call it, which is strictly smaller than alpha. Okay. And now we proceed like that. We take two values alpha n, an and bn, and an is exponential of n times exponential of n, and bn is essentially an multiplied by e to the power of n. Yeah? And then you define your epsilon as 1 over root n. If t is in this interval a and bn, it's minus 1 over root n. If we still go xn further, and outside all these intervals it is just 0. So what do you do? Over most of the time, this behaves perfectly well, yeah? Like a Pareto variable. But by and then something happens, yeah? And the effects vanish once again then, and however, well, occasionally something happens, and now we can check things and calculate L of bn explicitly. This is just by solving integrals. And what do we get? That's x to x of root n, which is about the same as x of log bn to the power of 1/2, which shows that in general, even if the random variable we have constructed is somehow strange, such an error cannot be avoided. And in particular, you can also verify that this random variable satisfies this condition here, which is just one of these characterizations of the Pareto tail growth, moment growth. So we are done. Of course, this proof can also be generalized, and it has a few more aspects. For instance, the proof gives regularly varying tails with index minus alpha. If you are familiar with regularly varying functions and slowly varying functions, it is, I mean, it's inspired by these constructions, right? These Kawamata theory. And it can, of course, be modified to other errors. I've just picked up one here to make the whole thing more understandable in a way. And in particular, we can also modify this, we can smoothen this a little in such a way that the random variable is even log convex. Yeah? So log convexity does not ensure the error not to occur, so to say. Okay. Now I still wanted to tell a little about concentration inequalities in a sketchy manner, so to say. And first we have to recall some basic aspects. So take any two independent subportion random variables. Then it is easy to see that the square of x1 or also of x2 and also the product of these two independent factors, these are both sub-exponential random variables. So the tail behavior of the square and the product of two independent factors is the same. However, what happens if we take these Pareto random variables? Now, if you square one of them, then it's a very basic calculation that in fact you still have a Pareto random variable, but the tail goes heavier, becomes heavier because you now have this alpha hammer. That's immediately. And what happens if you take the product of two independent factors? Well, then the LP norm squares. Yeah? But if you translate this into tails, yeah, by this Chebyshev-type arguments, then you actually do not get these heavier tails, but your tail behavior only worsens by something logarithmic. Yeah? And the moral of all this is that in the Pareto case, squares have much heavier tails than products of two independent variables, and this is already a crucial difference to the standard case. And only to the subportion case, but also to all this alpha exponential stuff, right? That's basically the same, but here something different happens. And now let's have a look at linear forms. To see what happens further. So let us symmetrize this time Pareto random variables for some alpha which is greater than 2, because all the two values assume that p is greater or equal to 2. And so some coefficients are a1 to an. And then you can apply theory from the 90s by Echenko, Montgomery Smith, and Oleszkiewicz, which gives you very fine p-bounds for this stuff here. And if you look at this, this suggests a tail behavior very roughly. This is anything but correct what I've written down here, but it's more heuristically. Well, here you have something of Pareto-type. So here you should have something like t 1 divided by t to the power of alpha, which scales with, well, approximately the alpha norm of A. The alpha norm of the coefficient vector A. And here, by contrast, we have something sub-Gaussian, because root of p means sub-Gaussian tails. So here you should get sub-Gaussian tails which scale with the 2 norm of the coefficient vector. And indeed, something like this, I mean, this has to be made preface, but something like this holds true, and it's the Fugner-Gaev inequality, also from the 70s. However, you have some problem if you want to apply standard techniques to get this out of this, because you can already see here. I mean, we can only access all this up to for p smaller than alpha, right? And in principle, you have sub-Gaussianity requires this to be valid for every p, for every p greater or equal, say 2 or something like that. So these are heuristics which are not so easy to make precise. And in particular, this is interesting if you want to iterate this, which is what matters if you want to access higher orders. And one way out of this is to worsen all this a lot by estimating all this by the worst possible cases, which is the 2 norm of A times this Pareto-type. Well, now it's a lot worse, but we have something we can work with. And indeed, this is what we now do. The rest are basically standard arguments for everybody who's familiar with all this stuff. You take any type of any random variable with sub-Pareto types, and then you can decouple them, you can symmetrize them, and you can take Pareto random variables as so to say a reference measure. And then you can start the usual iteration procedures in order to deduce concentration bounds for functions of this type, even if you have to recenter them, of course. I omit the details here. Now, it works like that, and in particular, now I come back to the beginning of my talk. Finally, we do get something like a heavy-tailed Hanson-Wright inequality, which looks like that. I mean, here you have this Pareto-type tail growth, and if you are on the off-diagonal of the matrix, the power is alpha, and if you're on the diagonal, the power is alpha half, which is, I mean, clear after what I've said about the behavior of squares and products of independent factors, right? And of course, for any order d, you get something similar. Which then depends on, so to say, on which level of your generalized diagonal you are. Okay, so this is what I've written here. Now, maybe to conclude, of course, there are open questions, and the immediate one is that this, I mean, finally I was happy to have this bound, and it's somehow interesting because you have these two levels, which do not appear, of course, in classical cases. However, this should not be the end of the story. With this Fugner-Gaev stuff, there's every reason to believe that this can be made a lot sharper. But currently, I do not know how. Okay, and this is everything I wanted to tell you. And,